In the polar night of the high Arctic, nothing should feel hidden. Ice reflects light. Satellites pass overhead dozens of times a day. Every major expedition is logged, funded, reviewed, and archived. And yet, in 1987, something recorded by a legitimate scientific team entered the paperwork, and then slowly vanished from the conversation. Not erased, not denied, just no longer discussed. The entry was brief, technical, almost dismissive. A note describing an anomalous structure detected beneath a moving ice sheet. Geometrically consistent, clearly bounded, and, according to the report, non-essential to the mission's primary objectives. That phrase, non-essential, would later become the quiet reason nothing followed. Because in science, what gets investigated isn't always what's discovered. It's what institutions decide is safe to pursue. Tonight, we begin with a single line in a decades-old Arctic report and follow what happened after scientists noticed something they were not prepared to explain. The late 1980s marked a transitional period in polar research. The Cold War was still shaping funding priorities, but scientific collaboration across borders had quietly increased. Arctic expeditions were no longer only about territorial presence. They were about climate modeling, ice dynamics, and understanding how the polar regions influenced the global system. The expedition in question was not secret. It involved researchers from multiple institutions, operating under a clearly defined mandate to study ice movement, subglacial topography, and stress patterns within large ice sheets. Tools included ground-penetrating radar, seismic sounding, and early satellite-assisted positioning. In other words, this was not a mission looking for surprises. And yet, buried within the technical appendices of the final report is a short section describing an unexpected radar return beneath the ice. The language is careful, conservative. It notes that the signal was persistent across multiple passes and displayed edges inconsistent with surrounding formations. No claims were made about origin. No conclusions were drawn. The structure was cataloged, assigned coordinates, and, critically, excluded from further analysis on the grounds that it fell outside the project's scope. On paper, this was normal procedure. In practice, it was the moment the story fractured. Within a year, follow-up expeditions returned to the region. Their publicly stated goals overlapped with the earlier mission: ice thickness, basal conditions, movement rates. But their routes shifted. Subtly at first. Transects that would have crossed the original coordinates were adjusted by tens of kilometers. There was no announcement, no explanation. Internal planning documents, later referenced in secondary sources, show discussions about data redundancy and logistical efficiency. Yet those same routes had been deemed efficient just a year earlier. At the same time, access to portions of the original dataset became restricted. Not classified in the military sense, but moved behind institutional permission walls. Still accessible, technically, just no longer convenient. Engineers who reviewed the radar data reportedly disagreed on interpretation. Some suggested uncommon but natural subglacial formations. Others pointed out that the geometry appeared too regular to be easily dismissed. Geophysicists raised a different issue entirely. Physical properties inferred from the signal, density contrasts, reflectivity, did not align cleanly with established models of ice-bed interactions in that region. Again, no conclusions were published, and that absence is important. In science, unresolved anomalies are often where the work accelerates. Papers invite debate. Replication follows. Here, the opposite happened. The anomaly was logged, acknowledged, and then quietly set aside. Funding patterns shifted soon after. Grants associated with deeper subglacial mapping were redirected toward broader climate modeling. Ice dynamics research continued, but at scales that smoothed over local irregularities. The structure remained in the records, but no longer in the narrative. By the early 1990s, the coordinates tied to the original detection had become strangely quiet. Not erased from maps, not restricted, just avoided. Modern ice mapping initiatives, with far more advanced technology, routinely passed near the area without directly surveying it. There is no memo explaining why. No formal decision stating the site was unimportant or too important. Just a pattern of omission that raises an uncomfortable question. In one of the most monitored environments on Earth, how does something documented simply stop being followed? In the next part, we'll look closer at the data itself. What was actually recorded in 1987, how it compares to known subglacial formations, and why even cautious scientists began to disagree on whether this was something nature could easily produce. Because sometimes the most revealing clue isn't what science finds, it's what it chooses not to revisit. The anomaly didn't disappear because it was disproven. It disappeared because it was never resolved. And to understand why, we have to return to the raw data itself, to what the instruments actually recorded beneath the Arctic ice in 1987, before interpretations, before institutional caution, before silence set in. Because buried inside those radar returns is the real reason scientists quietly disagreed, and why no official conclusion was ever written. Ground-penetrating radar is not a tool prone to imagination. It does not see shapes the way the human mind does. It measures signal reflections, changes in density, composition, and structure, and converts them into data profiles. In polar research, this method is routine. Over decades, scientists have cataloged subglacial lakes, mountain ranges, sediment layers, and bedrock features with increasing precision. The Arctic, while extreme, is not unknown terrain, which is what made the 1987 reading so uncomfortable. The initial radar sweep detected a sharply bounded region beneath the ice, its edges returning signals that dropped and rose abruptly, unlike the gradual transitions typical of natural formations. The signal's strength was consistent across multiple passes, ruling out transient interference. Most importantly, the structure appeared stable relative to the moving ice above it. That detail matters. Ice sheets flow, slowly but relentlessly. Anything embedded within or formed by ice dynamics tends to shift, deform, or blur over time. This signal did not. Its boundaries remained fixed relative to the underlying coordinate system, suggesting it was anchored to whatever lay beneath. That alone placed it outside the expected behavior of ice-driven features. As the data circulated internally, interpretations diverged. One group of engineers argued for an unusual geological formation, perhaps an isolated bedrock dome or a compacted sediment structure with uncommon reflectivity. Rare, but not impossible. But geophysicists raised objections. First, the inferred density gradient was inconsistent with known rock types in that region. Second, the geometry was problematic. Natural subglacial features tend toward irregularity, shaped by pressure, erosion, and thermal variation. This structure exhibited near-linear boundaries over distances difficult to reconcile with stochastic natural processes. No one claimed it was artificial. That assumption was never seriously proposed in official discussions. The problem was simpler and more troubling. There was no satisfying natural explanation either. In science, unexplained data is not unusual. But there is a difference between not yet understood and structurally incompatible with current models. This anomaly leaned toward the latter. One internal note, later referenced indirectly in secondary analyses, described the feature as model-resistant, not impossible, but inconvenient. Accepting it would require revisiting assumptions about subglacial mechanics in polar environments. And revisiting assumptions costs time, money, and credibility, especially when the anomaly had no clear relevance to the expedition's original objectives. At this point, the decision not to pursue the structure can be understood as pragmatic. Expeditions are finite, budgets are tight, missions have deliverables. But the next development complicates that narrative. When subsequent surveys were planned, updated radar systems were deployed, systems capable of far higher resolution than those used in 1987. In theory, these would have been ideal for revisiting the anomaly. Yet the survey grids were drawn to avoid it, not by hundreds of kilometers, sometimes by less than 50. Close enough to appear coincidental, repeated often enough to form a pattern. When questioned years later, researchers cited logistical constraints, weather variability, and shifting research priorities. All reasonable explanations. Individually. Collectively, they form a curious absence, especially given that modern ice mapping projects routinely investigate anomalies far smaller and less defined than the one recorded in 1987, which raises a deeper question. Why did this specific structure fail to generate curiosity? Or perhaps more accurately, why did it generate too much? Scientific institutions are designed to reduce uncertainty, not amplify it. They rely on peer review, consensus, and incremental progress. Anomalies that resist integration can become liabilities. This doesn't require conspiracy, only caution. If a feature cannot be explained within existing frameworks, pursuing it risks producing results that are difficult to publish, defend, or fund, especially when the potential outcomes are ambiguous rather than revolutionary. There was no clear upside to chasing the anomaly, but there was risk. Risk of wasted resources. Risk of public misinterpretation. Risk of opening questions without answers. So the structure remained in the archives, acknowledged but inert. Not hidden, just dormant. Yet one detail continues to unsettle those who've revisited the case decades later. The coordinates. Despite advances in satellite imaging and ice-penetrating radar, the region around the original detection remains curiously underrepresented in high-resolution public datasets. Not blank, but blurred, smoothed, averaged, enough to conceal fine structure. Which brings us to the question that changes the story from scientific footnote to institutional mystery. If the anomaly was merely irrelevant, why does it still shape where modern research looks and where it does not? In the next part, we'll examine how data classification, access restrictions, and funding decisions quietly determine what science sees and what it never has to explain. Because sometimes the most powerful filter isn't censorship, it's priority. Science often presents itself as a pure search for truth. But in practice, truth only moves forward when someone pays for it to move. And in the case of the Arctic structure logged in 1987, money didn't just slow the investigation, it quietly redirected it. To understand how a documented anomaly can remain unresolved for decades, we have to step away from the ice and look at the systems that decide which questions are worth asking in the first place. Large-scale polar research is expensive. Aircraft hours, satellite time, specialized instruments, and multinational logistics require sustained funding. That funding does not appear spontaneously. It flows through agencies, committees, and strategic priorities. In the late 1980s and early 1990s, those priorities shifted dramatically. Climate modeling rose to the top of the agenda. Ice sheet mass balance, global sea level projections, and long-term temperature trends became the dominant justification for Arctic research. Funding proposals increasingly emphasized regional averages, large data sets, and predictive models. Local anomalies, especially ones without immediate climate relevance, were harder to justify. The structure beneath the ice did not threaten coastal cities. It did not change temperature projections. It did not fit neatly into climate narratives that policymakers were eager to support. In grant language, it lacked societal impact. That single phrase can quietly end an investigation. Funding records from the period show a clear pattern. Projects focused on broad ice dynamics expanded. Programs dedicated to fine-scale subglacial mapping narrowed or merged into larger initiatives. This did not eliminate the tools needed to revisit the anomaly. It deprioritized them. Researchers involved in early Arctic radar work later described a growing pressure to align proposals with predefined outcomes. Not falsified outcomes, but expected relevance. A question without a clear endpoint was a risk. The anomaly posed exactly that problem. It demanded attention without offering resolution. And unresolved attention is dangerous in institutional science. It can stall careers, delay publications, complicate messaging. So, instead of being rejected outright, the structure was absorbed into the background. Its data preserved, its implications unspoken. Data does not speak for itself. It requires framing. When data sets are published, they are accompanied by interpretations, confidence intervals, and contextual explanations. Anomalies that cannot be framed often appear only in appendices, or not at all. The 1987 structure lived in that liminal space, referenced but not discussed, recorded but not interpreted, available but not emphasized. Over time, newer datasets layered over the old ones. Lower resolution averages replaced sharp local features. This is standard practice for modeling, but it has consequences. Fine details disappear, and once they disappear from commonly used datasets, they stop shaping questions. A future researcher unaware of the original detection sees a smoothed region and moves on. Not because something is hidden, but because the anomaly no longer appears anomalous. This is how scientific blind spots form. Not through suppression, through accumulation. There is another reason the structure remained untouched. Reopening it would reopen everything around it. Revisiting the site with modern instruments would force comparison with older data. Differences would have to be explained. Questions would arise about why the feature was not followed earlier. Institutions are cautious about retroactive scrutiny. Admitting uncertainty is acceptable. Admitting long-standing omission is more complicated. No single decision-maker chose silence. No meeting voted to avoid the coordinates forever. But once a pattern sets in, once expeditions plan around an area, once funding flows elsewhere, reversing course becomes difficult. Not politically impossible, psychologically uncomfortable. Yet, the story does not end with funding charts and institutional inertia. Because despite decades of avoidance, the anomaly never fully disappeared. Its coordinates still exist in archived metadata. Its signal still appears, faintly, in reprocessed datasets. And a small number of researchers, working far from the spotlight, have quietly noted that the original readings remain inconsistent with known subglacial behavior, which leads to the most unsettling question so far. If the structure was simply irrelevant, why does it continue to resist explanation every time it is rediscovered? In the next part, we'll examine what modern technology should be able to see beneath the Arctic ice today, and why, despite unprecedented resolution, certain details remain conspicuously unresolved. Because sometimes progress doesn't clarify mysteries. It sharpens them. By the time modern satellites began mapping the Arctic in extraordinary detail, the mystery should have ended. Higher resolution, better instruments, faster processing. If something unusual existed beneath the ice in 1987, Today's technology should have clarified it, or erased it entirely. Instead, it did something far more unsettling. It made the absence harder to explain. Since the early 2000s, polar observation has entered what many scientists call the transparent era. Ice-penetrating radar mounted on aircraft can resolve subglacial features down to tens of meters. Satellite altimetry detects minute surface changes that betray structures below. Gravity mapping reveals density anomalies invisible to conventional imaging. In theory, nothing large and stable beneath the ice should remain ambiguous, especially not after decades of repeated coverage. And yet, when modern datasets are examined around the coordinates logged in 1987, something peculiar emerges. Not a clear image, but a persistent lack of one. The region is not missing from maps, it is present, but generalized. Data is averaged, resolution drops. Fine-grained detail fades earlier than it does in neighboring areas. This is subtle, invisible to non-specialists, but to those familiar with polar datasets it stands out, not as concealment, as avoidance by design. To understand why this matters, we need to clarify how modern mapping actually works. High-resolution surveys are rarely global. They are targeted. Aircraft flight paths are planned based on scientific priorities. Satellite modes switch depending on what researchers request. Resolution is a choice, not a constant. When an area is not selected for detailed study, it doesn't disappear. It becomes statistically quiet. And that is exactly what appears to have happened here. Despite advances that routinely resolve subglacial lakes and mountain ridges, the area surrounding the original anomaly has never been the focus of a dedicated, high-resolution campaign. Again, no prohibition exists, no official restriction, just a long sequence of decisions pointing elsewhere. Which brings us back to a critical detail from 1987, the structure's stability. Modern ice flow models show that ice in this region moves measurably over decades. Yet the anomaly's inferred position, when reanalyzed against contemporary coordinate systems, appears remarkably consistent. That consistency should be testable. It hasn't been. If the structure is natural, modern surveys should show deformation, erosion, or interaction with the moving ice. If it is bedrock, it should integrate into regional geological models. But those models remain unresolved in precisely this zone. Some researchers suggest the explanation is mundane: insufficient data density, poor signal-to-noise ratios, logistical constraints. Each explanation is plausible. What strains plausibility is their persistence. Decades of technological progress have eliminated similar uncertainties elsewhere. Yet here, ambiguity remains oddly resilient, which raises a question that scientists are trained to ask, but institutions often avoid. What would it mean if the structure is real, stable, and incompatible with current models? Because that answer doesn't just affect one anomaly. It affects how we interpret everything around it. Reinvestigating the site today would not simply confirm or deny a past reading. It would retroactively validate a decision point from 1987. If the anomaly is confirmed, then decades of omission become a subject of scrutiny. If it is disproven, the original detection must be explained as error, raising questions about the reliability of similar datasets from that era. Either outcome creates discomfort. Scientific institutions prefer uncertainty that fades quietly over time. They are less comfortable with questions that resurface sharper than before. And modern technology has a way of sharpening questions. It is important to emphasize what this story is not. There is no evidence of a coordinated effort to suppress findings. No documents ordering silence. No locked vaults of forbidden data. What exists instead is a convergence of incentives. Funding favors relevance. Research favors continuity. Careers favor predictability. An anomaly that refuses to resolve threatens all three. So it remains where it is, documented, acknowledged, and perpetually postponed. Not forgotten, just never addressed directly. But there is one final layer to this story, one that shifts it from institutional behavior to something more fundamental. Because when independent analysts reprocess older Arctic datasets using modern algorithms, they sometimes notice something disturbing. The original 1987 signal doesn't weaken with reinterpretation. It clarifies. Edges sharpen. Boundaries become more distinct. And the feature's resistance to natural explanation becomes harder, not easier, to dismiss. Which leads us to the most difficult question yet. If the data itself is becoming clearer with time, why does our willingness to confront it seem to be fading? In the final part, we will confront what the structure most likely represents, not by speculation, but by elimination, and why acknowledging that conclusion would challenge the quiet assumptions that keep modern science functioning smoothly. Because sometimes the most unsettling discovery isn't what lies beneath the ice. It's what lies beneath our decision not to look. Every mystery eventually reaches a narrowing point, where possibilities collapse, not into certainty, but into a smaller and more uncomfortable set of explanations. By now, we know what the Arctic structure is not. It is not a transient radar artifact. It is not an ice-driven deformation. It is not easily absorbed into existing geological models. What remains is not a revelation, but a reckoning. Because when science cannot explain something by addition, it explains it by elimination. And elimination has led researchers, quietly and reluctantly, toward conclusions they are not eager to publish. Let's be clear about the ground rules of this story. There is no verified evidence that the structure is artificial. There is no confirmed proof of non-natural origin. There is no missing document that reveals the truth. What does exist is a narrowing field of explanations, and a persistent failure of natural models to fully account for the observations. When independent analysts reprocessed the 1987 data using modern signal enhancement techniques, something unexpected happened. Noise dropped away. Margins sharpened. The feature did not dissolve into randomness. It gained definition. In science, false positives usually degrade under scrutiny. Real signals often become clearer. This one did. And that distinction matters more than any speculation ever could. Researchers attempting to reconcile the structure with the known geology encounter a cascading problem. If it is bedrock, its geometry is anomalous. If it is sediment, its density contrast is too sharp. If it is a subglacial lake, its reflectivity and stability don't match liquid behavior. If it is a glacial artifact, it should migrate or deform. Each explanation fails for a different reason. Not dramatically, quietly, technically, and when multiple independent models fail in different ways, science faces a choice: invent a new mechanism or admit a blind spot. Blind spots are harder. They suggest that our understanding of subglacial environments, especially under extreme pressure and time, is incomplete. That possibility does not threaten public safety, but it does threaten confidence. Modern science operates on trust. Not blind trust, but trust that anomalies are eventually resolved, incorporated, or discarded through replication. This structure resists all three outcomes. Resolving it requires focused study that no one is incentivized to lead. Incorporating it requires modifying models that work well elsewhere. Discarding it requires explaining why consistent, persistent data should be ignored. So, the system defaults to stasis. The anomaly remains acknowledged but inert, present in the archives, absent from discourse. And over time, absence becomes normal. There is another reason the structure remains untouched, one rarely stated aloud. Revisiting it would force science to admit uncertainty in a domain it presents as increasingly precise. The Arctic is often portrayed as one of the most comprehensively monitored regions on Earth. Satellites, sensors, models, all feeding a narrative of total observation. A stable, unexplained structure beneath the ice complicates that story. It suggests that even with modern tools, there are features we detect but do not understand, and perhaps do not fully want to. Not because they are dangerous, but because they don't fit. So, what does the data actually suggest? It suggests the presence of a stable subglacial feature with defined boundaries, resistant to ice dynamics, and inconsistent with known geological categories. That is not a conclusion. It is a constraint, and constraints are powerful. They shape what future explanations must account for. Any satisfactory explanation must explain the geometry. It must explain the stability. It must explain why modern surveys still fail to resolve it clearly. So far, none do. This is where the story must end. Not with answers, but with clarity about the question itself. The Arctic structure was logged. It was not disproven. It was not followed. And it remains unresolved. Not because of secrecy, but because acknowledging it fully would require science to pause, to say, "We don't know yet," in a space where certainty is assumed. And perhaps that is the most unsettling possibility of all, that in one of the most observed places on Earth, something can be detected, documented, and then quietly set aside. Not out of fear, but out of inconvenience. The structure beneath the ice does not demand belief. It demands attention. And for nearly 4 decades, attention has been the one thing it has not received.